Most developers use Git every single day and treat it like a magic spell. You type git add, git commit, git push, and if nothing explodes, you don't ask questions. But here's the secret. Git is not magic. Underneath, it's one of the simplest and most beautiful pieces of software design you'll ever see. It's just a little key value database made of files, plus a handful of text files that point at things. And today we're going to prove that by taking apart the .git folder with nothing but the command line. By the end, we will literally build a commit by hand, without ever running git commit. Let's start from absolute zero, an empty folder. I'm going to run git init playground, and then we're going to immediately break the #1 rule of Git tutorials and go look inside the .git directory it just created. So dir.git, and look how small this is. 4 folders and 3 files. Hooks is just sample scripts. Info is minor config. The 2 that matter are objects and refs, plus that little file called head. This is the entire anatomy of a Git repository. Everything Git will ever know about your project lives in here. And that head file? It's 23 bytes. Let's print it. refs/head/master. That's it. Head is a text file containing a path to another file. Remember this moment, because when we get to branches, this tiny file is going to explain about 90% of Git's behavior. Now for the star of the show, the objects folder. This is Git's database. And the fundamental operation of that database is, give me some content, and I'll give you back a key. Git calls it hashing an object. Let me feed it the string hello Git, using the hash object plumbing command. That long hex string is a SHA-1 hash of the content. It's deterministic. The same bytes will produce D85F9D on my machine, on your machine, on a server in Tokyo, every time, forever. This is the single load-bearing idea in all of Git. Content is addressed by its hash, not by a file name, not by a date, by what it is. So far we only computed the key. Now let's actually store it by adding -w for write. Same hash comes back, but this time, something changed on disk. Let's look inside the objects folder. There's a new subfolder called D8, the first 2 characters of our hash. And inside it, a file named with the other 38 characters. Git shards objects into 256 subfolders just to keep directory listings fast. So our content now lives at objects/D8/ the rest of the hash. This is the whole database. Folders and files, named by hashes. And to read things back out of the database, there's cat file. -t asks for the type of an object, and Git says this one is a blob, which is just Git's word for a chunk of file content. -p pretty prints the content itself. Hello Git. Round trip complete. Store by hash, retrieve by hash. Notice I only typed the first 6 characters of the hash. Git is happy with any unique prefix, which is why every Git tutorial and every Git log you've ever seen shows short hashes. They're just abbreviations of these database keys. But I don't want you to take Catfile's word for what's in that file. Let's read the raw bytes ourselves. The object file is compressed with zlib, so I'll use a 1-line Python script to decompress it and print exactly what Git wrote to disk. And there's the entire storage format in 1 line. The word blob, a space, the content length, a null byte, and then the content. That's it. That header is also part of what gets hashed, which is why a blobs hash isn't just the SHA of your file contents. And notice the 11, our 9 characters plus a carriage return and new line that PowerShell's pipeline added. The hash proves it. Git hashed exactly the bytes it received, invisible characters included. So when people say Git is a content-addressed file system, this is the whole trick. A header, zlib compression, and a SHA-1 hash as the file name. You could re-implement this storage layer in an afternoon. And honestly, doing that is one of the best programming exercises there is. Okay, but nobody uses Git by piping strings into hash object. You edit files, and you run git add. So let's connect the plumbing to the porcelain. I'll create a real README file in the editor. Just a heading my project. Now git add README. And here's what git add actually does. 2 things. It writes the file's content into the object database as a blob, exactly like our hash object command did. And it records that blobs hash in a file called the index, the staging area. We can see the index with git ls files --stage. Read that line. File mode 10644, a normal file. Then the blob hash f86702 and the path readme.md. The staging area is literally a list of rows like this. Path plus the hash of the exact content you staged. When people say git stages a snapshot, not your working file, this row is what they mean. If I edited readme right now, the index would still point at the old blob until I ran git add again. Time to commit. Git commit -m add readme. One file changed. But what did that actually create in our database? Let's ask Packfile to pretty print whatever head points at. And here is a commit object in the flesh. It is tiny. A tree hash, an author, a committer, and the message. That's the whole thing. Notice what's not here. There's no diff, no patch, no list of changed files. A git commit does not store changes. It stores a pointer to a complete snapshot, and that snapshot is the tree. So let's follow the pointer. Packfile -p on head's tree. And a tree object is just a directory listing. One row per entry. Mode, type, hash, name. Ours has a single row, pointing at the readme blob we already know by name. A tree is a folder, a blob is a file, and both live in the same object's database. It gets more interesting with a second commit. Let me add some actual code, a source folder with a tiny app.py inside. Add it, commit it, and print the new head commit. And look, a new line appeared that wasn't in our first commit. Parent, followed by a hash. And that hash, EB97B6E, is exactly our first commit. This is how history exists in Git. Not as a log file, not as a timeline stored somewhere. Every commit simply holds the hash of the commit that came before it. And check out the new tree. 2 rows now. The readme blob, unchanged, same F867 hash as before. And a second row of type tree for the src folder. Trees can point at other trees, which is how nested directories work. It's a recursive structure, folders all the way down. And of course we can follow that src pointer too. Packfile on the src trees hash, and there's the inside of the folder. One row, the blob for app.py. Any file, in any folder, at any point in history, is reachable by walking hashes from a commit. And pause on that unchanged readme hash for a second, because it reveals something huge. The second commit did not copy readme. Both commits, through their trees, point at the exact same blob. Files that don't change are stored exactly once, no matter how many thousands of commits reference them. People say Git stores snapshots, and you imagine it copying your whole project every commit. It doesn't need to. Content addressing gives it deduplication for free. So when you run git log, all Git does is start at head and walk the parent pointers backwards, printing as it goes. 2 commits, newest first. The log isn't stored anywhere. It's computed from the graph every time. Let me draw the whole picture we've built so far, because it's genuinely elegant. At the top, our 2 commits. The newer one points at the older one through its parent field. That chain of pointers is what you've been calling history all these years. Each commit points at exactly one tree, its snapshot of the project root. The tree points at blobs for files, and at other trees for subfolders. Our src tree points at the app.py blob. And that's all 4 object types Git has, by the way. Blobs, trees, commits, and annotated tags, which we're skipping today. 4 types, 1 database, everything addressed by hash. When something in Git confuses you, the fix is almost always to come back to this picture and ask, which object is pointing where? Which brings us to branches. And I need you to brace yourself, because this is the part where Git's reputation for complexity completely falls apart. What is the branch master really? It's a file. Let's print it. 40 hex characters and a new line. 41 bytes. That's the entire branch. It's a text file whose content is the hash of one commit, the tip. A branch in Git is a sticky note that says, this line of work currently ends here. So creating a branch, that just writes one more 41-byte file. Git branch feature, and dir the refs folder. 2 files now, feature and master. And print the new one. It contains the exact same commit hash. Both sticky notes point at the same tip. This is why creating a branch in Git takes a millisecond even in a repository with a million commits. Nothing is copied. Ever. And remember our 23-byte head file from the very beginning? Watch what happens when I switch to the feature branch and print head again. It changed. Ref, refs, heads, feature. That's what checking out a branch is. Git updates one line in one text file, then makes your working folder match whatever that branch points at. Head answers one question, where am I? Branches answer, where does each line of work end? Everything else is the object database. This also finally explains the famous detached head state that scares every beginner. Watch. I'll check out a raw commit hash instead of a branch name. Git prints its big warning. And now look at the head file. It doesn't contain a ref path anymore. It contains a commit hash directly. That's all detached means. Head is pointing straight at a commit instead of at a branch. Nothing is broken. Your sticky note is just floating. Switch back to a branch, and the ref path returns. And now, the final boss. I claimed at the start that git commit is just a convenience wrapper, and that we could forge a commit ourselves straight into the database. Time to pay up. We'll use only plumbing commands. Step 1. Write a blob for a new file's content. Step 2. Stage it by hand. Update index, --add, --cache info, then the mode, the blob hash, and the path notes.txt. And if we list the stage now, there it is, sitting right between readme and app.py, even though no file called notes.txt exists in our working folder. We staged pure database content. Step 3. Turn the staging area into a tree object with write tree. It hands back the hash of a brand new tree, a snapshot containing all 3 entries. Step 4. The forgery itself. Commit tree takes that tree hash, a parent, which I'm pointing at the current head commit, and a message piped in. Commit made by hand. And it returns a commit hash. We just created a commit object without git commit anywhere in sight. One problem. That commit exists in the database, but nothing points at it yet. It's floating. So, final step, we move our branch's sticky note onto it with update ref. And now, the moment of truth. Git log. Commit made by hand, sitting at the top of the history, as real as any commit ever made. Because that's all git commit does. Write tree, commit tree, update ref, wrapped in one friendly command. You've now seen the entire pipeline with your own eyes. Blob, index, tree, commit, ref. There is nothing else. One last mystery, for completeness. If every object is its own little file, doesn't a 10-year-old repository with a million objects turn into a file system nightmare? Let's ask Git how many loose objects we have right now, with count objects. 8 loose objects. Now watch what happens when I run git gc, Git's garbage collector and optimizer. Count drops to 0, and in pack becomes 8. All our objects just moved into a pack file. A pack file is a single compressed archive holding many objects, with an index file next to it for fast lookup. And inside packs, Git finally does store deltas, differences between similar objects, to save space. So the mental model stays clean. Logically, Git is always full snapshots. Physically, Packfiles compress the redundancy away. You get snapshot simplicity and delta efficiency at the same time. By the way, this picture also explains 2 things every developer has felt in their bones. Why deleting the .git folder nukes your entire history. All of it lives in there and nowhere else. And why cloning a repository gives you the complete history offline. A clone isn't a checkout of the latest version. It's a copy of the whole object database, every commit, every tree, every blob, straight onto your disk. Your laptop holds exactly what the server holds. Let's put the whole machine back together. Git is a content-addressed object database. Blobs hold file content, trees hold directory listings, commits tie a tree to its parents and an author. On top of that database sit the refs. Branches, 41-byte files pointing at commits. And head, one more tiny file pointing at a branch. Every Git command you've ever run is just manipulating this structure. Commit writes objects and moves a ref. Check out moves head. Merge writes a commit with two parents. And once you see it, Git stops being a magic spell you memorize and becomes a system you can reason about. Everything you watched today was a real terminal session, and I really do recommend making a throwaway repo and spelunking through .git yourself. It's a rite of passage. If this demystified Git for you, a like genuinely helps the channel, and subscribe for more deep dives. Next time, we're writing an HTTP server from a raw socket by hand and watching a browser talk to it. See you there.